So, good morning, everyone. Week number 5. I see a little bit more people than last time in the chat. This is encouraging, so I'm not speaking to an empty room. That's rather nice. So today we, of course, start again with the exercise sheet, and I'll discuss a little bit about the exercise sheet. Good. So exercise number 5 was all about references. And the first question was this updated, let me just quickly scroll that up for you, was the updated update function in a way like this. And the question was, would it behave the same? So let's look at that update function. So how to kind of address this. So how to find out if this would behave the same. Well, we can use it. So just to have it on my sheet of paper again. So the other update function was update lambda a not array. Oops. Lambda m would be the index of the thing to be updated, and lambda y would be lambda v, would be the natural number of the value to update it to, and the body of this would be an reference update of a, and it would be setting it to lambda n not if equal. Close the blinds for a bit more. Equal m, n, then v, else dereference a, n. So there wouldn't be this let old in there anymore, and how would it behave? So how would we use this? Well, let's say we have an array called A, or let's call this array B maybe. So B is of type not array. Let's assume that we have that, and let's use that now. So we use update on this lambda array, and we say on position 2 we would like to have a 42. So what happens then? Let's find out what that means. So if we carry on all these things, it would be, this would in multiple steps evaluate to something like this. So B is assigned to lambda n not if equal m would be 2, 42, no, n, n, it's not v, then v, else dereferenced b, n. Oh, looks fine. Well, this array would be now set to B, and we would be fine. But then if we would use this array, what would happen? So if we now say, okay, let's say we dereference B and look up 2, what would happen then? Well, it would exchange n by 2 in this, and equal 2 and 2 is true. Then this would in multiple steps evaluate to v, and this is also 42 here and 42 here. So this would work somehow fine. But if we say, okay, let's look up 1, what would happen then? well, let's do that. Let's dereference that. That would be this. So, and then apply it. So this would rewrite to if equal to 1, then 42, else dereference be n. No? And, oops, sorry. And there you see it. You get to the branch and n would be 1. Yeah? And then this would evaluate in one step actually to dereference b1, which was the original term that you started in there. Yeah? And this of course would diverge. Now you would like get an infinite loop, so to say, and you wouldn't have any come to any conclusion at some point. So this update functionality does not work. Good. Because we will actually find the new function and not the old one. The let in the old update construct had the old function in it. And since we don't have this let in here, since we just reference b here, this would be the new function. This would be like a recursion, like an infinite loop here in this point. So that doesn't work. Good. Questions for this, maybe, before we move on? Good, if not, then let's just move on. Explicit deallocation. So what was the task here? Let me just quickly move a bit so we have more of the screen. Good. It's not in line anymore, but we'll manage. Okay. So the question here was show how explicit deallocation leads to a violation of type safety. And suppose the language provides a primitive tree that takes a reference cell, which is a location, as an argument and releases its storage so that the very next allocation of a reference cell will obtain the same piece of memory. How do we approach this? So remember that there was a hint, like remember that type safety means progressive preservation. So to show that something violates type safety, it is enough to give an example where one of these properties is violated. Okay, seems fair. Good. How to approach this? Let's do an example program. So this example program should use the free at some point, and of course, like we're talking about type safety and violations of type safety, so doing everything with the same type would probably not help very much. So let's construct a little bit something. So let's say we have let R be a reference to 0 in let S be R, so that we have an alias, and then let's say we free R sequenced. This is sorry, let me do this again. Free R, and then let's say let T be a reference to true in, and then let's assign false to T, sequence that, and get the successor of S. So we have R, which is a reference to 0. So let me look at the program state a little bit. So we have R, which refers to a cell in memory which contains a 0. Yeah. And then we have S, which is equal to R, which is a reference to the same memory cell. And then we free R. So this then is kind of freed again. And this cell is available. And then we construct T, which is a new reference, and it reuses the cell, and it uses it for true. In T false, then again this is overwritten with false. It's hard to read now, but it says now false, same memory cell again. And then we still have that reference S here, which is typed as a reference to a number, as you can see. So we can apply a successor of S. But in that memory cell, now there is a Boolean. So that would be not working. So this thing would actually not evaluate at some point. So this will eventually get stuck. So this is an eventually stuck, by the way. Because it tries to use the term successor of false, which would not work. You see that? And the interesting thing here is that aliasing here of S and R, because when we free R, of course we say, okay, R is not valid anymore. We can see that. So that makes R kind of illegal whenever it appears free in the remainder of the expression. So R does not appear anymore here, so we're good. But S appears. And this is actually not an academic example. And this is what happens with aliasing in languages where you do where you work with pointers a lot. When you do work with pointers are by standard, if you don't use something like a managed pointer in C or C++, these things are unmanaged. So these things just point, as we see here, into the memory cells, and it would not make a difference. Why does T point to the same cell as 0? Haha! This is the definition of the free operator. So look at the definition here. So suppose a language provides a primitive free that takes a reference cell as an argument, resets stores so that the very next allocation of a reference cell will obtain the same piece of memory. So when we did a free here, and this is sequencing, so this happens after. The next construction of a reference is here. So the very next allocation of a reference cell will obtain the same piece of memory. And this is actually something that you have in some definitions of free. And if you don't work with aliasing or do aliasing in a safe way, you would never notice, because this is just fine. But as you can see here, we can construct a program where this will actually not work. So this free in this definition as given here is hurting type safety. Yeah, but that's kind of this part in the exercise there. Good. More questions for 5.2. Good, nothing more? Then let's move on to 5.3. Okay, let me see. Oh, let me see. We do have more on one page here. So 5.3. What was 5.3? So the question was, we will see that in the lecture week 5, slide 47 following: that cyclic reference in a store can be tricky, can be a tricky thing, putting our type checker into an infinite loop if we are not careful. Can you find a term whose evaluation will create this particular cyclic store? Yeah, and hint, this might be later useful as a test case. I wonder what that would be for. Good. Let's look at cyclic references in the store. How would we do that? Well, of course, first we need some kind of reference, and as we've seen, like in the examples for cyclic reference, like functions are usually a good way to do this, because then our type checker would need to evaluate something in a way to actually find out if this would be working, and we don't want to do that, and so on. Like, we need to type functions and all a big mess. So let's do that. So let's do a let and say, because we want to reuse these references at some point, lets are very helpful. Let's do a reference R1. And let's make this a reference to a function that takes a natural number and returns a 0. Okay, so this is kind of a constant combinator that takes a parameter, disregards it, and returns 0. So basically constant 0. So let in, so and then the subterms. And then let's take another reference called R2 and construct that reference in a way that we would use this first reference. And the way to do this is to construct again a function and then use this other thing and dereference it and apply x to that thing. Because then we would like have a definition of what 0 would be, but doesn't matter in that case. We can do this because this returns a function, and then we can this returns a function, and this function returns 0, but we can like feed it something that it can ignore. And we did this in this case. So the result of this function will always be a 0 if we would evaluate this, but we don't know that yet during type checking. Remember that. And then we do another thing, and then we will do something that is a little bit tricky. So now we have to make it cyclic. So now we had this thing, which we stored, and then we referenced from R2 into R1. But now we need to make it cyclic, so R1 needs to reference back into R2. And how to do that is that we do an assignment to R1. And in that assignment, we define a new function and then use R2 in that new function, dereference that, and apply x to that, and sequence that with R2. And this would actually make a very hard cyclic store loop, because in order to type R2, we'd need to type R1, which is then overwritten by a new function, and then used again, and so on. It's like really convoluting, So this is then again reassigned, and then R2 is executed, which is then again using R1, which is then using R2, and so on. You see the loop happening here. You see the cycle. And this thing will actually put your type checker into an infinite loop if you are not careful at implementing that with typing. And this is a particularly useful example later on when you implement that stuff. When you implement references in your type checker, this would be something to really look out for. Good. Questions? For that particular exercise, or for any of that sheet maybe. Good. That does not seem to be an overly complex exercise, or let's say a longish exercise. The thought process might be a little bit longer. So maybe just one hint towards that. So the question here was to find something that puts ourselves into an infinite loop. And to do that is to create a cyclic reference. So constructed first thing, a reference that references the first thing. So a second reference reference the first thing, and then we need to go back from the first thing to the second thing. So we do an assignment that references the second thing. And since an assignment does not help us, we need to have some return value, and this is our 2 in this case. And this would actually be very much putting our type checker into an infinite loop if we don't carefully look about that. Good. If there are no more questions for the exercise, I'll propose that we do a 10-minute break before we start with the lecture. I think today will be a little bit of a short session because we already had some slides from today's lecture and the last lecture because it made sense. So it might be a little bit of a shorter day today. But anyway, the new lab will come out today, so you all might be pretty busy. By the way, after the lecture, I will publicize the results of the lab number 3. I've seen at least one person where the autograder didn't work. Again, I have to find out what that problem is. I don't know what the problem there is. Let me try again. Overall, the results look quite encouraging. Here and there, some points were missed, but more or less, this was all good. Good, then let's see you all in 10 minutes, and then we continue with the lecture.
Mais jus de swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée joue dans la rougette des zombies dans son chapeau. Dab dab, vidi 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 va. Les rois du jasmineux, marine in the bar. Innocent, sentimental, venez tous. Ces soirées jouent dans la rue, les rois du jasmineux.
Good. So welcome back. So our topic last time was subtyping, and we're going to continue that today with a discussion about how to implement this. Because the way to implement this is problematic, and we will see a little bit about this. Let me just quickly close the blind here. Gets a better picture. So, we closed last time with the bottom type, so the. Why did I say that? That doesn't have anything to do. Well, we closed with the arrays actually. Sorry. So subtyping does have a problem. So when the way we learned how to implement typing rules before is kind of a bottom to top way. So we implemented all the rules, and the matcher does its magic and matches the proper cases. For subtyping, we cannot actually do this, and this is mainly because of subsumption and the S-trans, the subtype transitivity rule. And why is this the case? Let's have a look at that. So this is the T-sub rule as we've learned it. So just as a reminder, whenever we say under the assumption of gamma, we can type T as S, and S is a subtype of T. We can also, under the same assumptions, type T under the assumptions of gamma. We can assume that T is also of type big T. No? Why is this problematic? Well, notice that T does not have a specific form. Whenever we match typing rules before, the let's say the conclusion did have some very unique form that we can easily match against. And this rule is so general that it's hard for us to actually match against that, because this basically applies to any term. No? And so that this means that T-sub basically matches every term anytime that is the case. So we would have to check the premises for that every time. And for many types, we will actually find subtypes. For instance, for each record type, we would always find the empty record type to be a supertype. In this case, we would also find a record type that has one field more that is a subtype, and we can construct this rule. We can construct a derivation by this rule. So this is not entirely good for our implementation, because we do not have kind of a limited space of choices. We do have a lot of choice here. And what's the problem with S-trans? So this was the other rule that I said is a little bit problematic here. So let's have a look at this one a little bit closer. So S and T are unbound. S and T can be kind of any types. It's hard to find that. And moreover, you would also don't know what U to choose, because there can be arbitrarily many in between. Let's say you found an S and a T that you want to check that for, but to find an U in between is rather hard, and to actually choose one. So we would never know when to apply it, or when to choose from a specific, choose a more specific rule when going from bottom to top. We would actually not know that anymore. And this, as you can have all now implemented a type system, you will should immediately find very problematic, because you cannot find the proper rules to implement for that. And again, as I said, I missed my own animation, so guessing U might be very hard, because the number might be infinite. Let's say S is the empty is a record with a lot of fields, and T is the empty record. then you would have like all permutations of S in there, and so on and so on and so on. And also if you have subtyping derivation where this is not so ideal, where you do have relations where you can construct arbitrarily many intermediate types, this would be very, very hard. So you cannot implement this properly from bottom to top. So what to do? The thing is, the rules that we learned right now were so-called declarative typing rules. And the thing about declarative typing rules is they work very well in proofs, as we've seen. They very naturally fall into place for the progress and preservation proof that we did, and we didn't have much work with that, to be honest. I mean, it was quite mechanic, it was quite the same thing as before. The thing is, we cannot implement those, as we've just seen. And for implementation, we need algorithmic rules, because they need to be kind of decisive. We need to be able to choose which path to take. And as you've seen, you can have like arbitrarily many different permutations of that. And if we would have something like an algorithmic typing rule that we can implement, where this decisiveness is, they must be saying the same, must be equivalent in a way, that our typing proofs are actually still valid also for the implementation case. And this introduces algorithmic subtyping. Because of this very specialty of subtyping, we separate now the type checker for the general type checking and the subtype checking. And the type checker then calls the subtype checker whenever expected and found types do not match. So let's say you have two types, and the type checker says, okay, they are not equal, they are not the same. So are they at least compatible with subtyping in one way or the other? And then they can call the subtype checker, and the subtype checker tells us, yes, that is the case, or no, that is not the case. And because we want to distinguish that a little bit, we take a new relation, we take the turnstile and put a little arrow at the end. And this is the algorithmic subtype relation. It's the same as before, but you do have this little notation in front of it that tells you, okay, it's algorithmic subtyping. Good. And also, we need to make the declarative system a little bit more compact to do that. And the first rule to do this, so we had like we looked at 3 record typing rules before, the sRCD width, the RCD depth, and the RCD perm rule. And we can do this a little bit easier. We can roll this into one, and this is the sRCD rule. This is the same thing, but for didactic reasons, we had these 3 rules that like separated these concepts out. You can express the same thing, and you can actually show the equality here if you like, in actually just one rule. And this just subsumes everything that we've heard before. And as subtyping is reflexive, you can use the SCD width and the RCD width and the RCD depth rule quite very much the same. And then you factor in the permutation with these different index sets as before, and just force that the labels are of the same. The labels are the same, but they can be in arbitrary other sequences. Then you basically subsume this in just one rule. Good. First, to show equality. That's what we talked about. We need to show that, like, if there is a subtyping relationship S a subtype of T derivable from the subtyping rules, including sRCD depth, sRCD width, and sRCD perm, but not sRCD, then it can also be derived just using sRCD, but not sRCD depth, RCD width, RCD perm, and vice versa in both directions. And you can prove this basically by straightforward induction. If you have something, if you have an empty schedule tomorrow at the public holiday, you can just freely do that. It's rather easy, also a little bit enlightening if you happen to have a little bit of trouble with the sRCD rule. Convince yourself and do the proof. And the funny thing about that, it eliminates the need for these three different rules. We can just go roll it into one and go from there. It's very much more elegant and compact. Good. And now we have a little bit of a problem with the S reflexive and S transitive rule. And the idea here is that S is subtype of S can be derived for every type S without using the S reflexive rule, and S is derivable from T is derivable if S is derivable. S is a subtype of T is derivable, then it can be derived without S trans. This is the idea of removing those. I did not explain this on the slide anymore. Interesting. Yeah, we meticulously added these to the type system in the last lecture, but as we actually don't need it, we can actually do very much without in the algorithmic subtyping system and just factor it in. We will see that in a second. I did have an explanation. I think I removed it from the slides for some reason, but interesting. Well, either way, it's one of a very, very smaller side effects of this thing. So this is algorithmic subtyping, and the algorithmic subtyping relation is the least relation on types closed under these rules. What does this mean? It's again a relation, and it is of course again the smallest relation, so the least relation on types. So we relate types to types here, and these are the three rules to do that. So let's look at those a little bit. So we can always find a top type that is a supertype of any type in algorithmic subtyping as well. We can have this SARCD rule. This is kind of the sRCD rule that we just imported, but translated into algorithmic subtyping. It is the same rule still, but whenever we had a subtyping relation, like in the premise here, or in the conclusion, we now have an algorithmic subtyping. Nothing else has changed basically in this SARCD rule. And then we have the arrow rule. This is also something that should be familiar from the last lecture. Also, it's basically the S-arrow rule, but with subtyping relation, with the subtyping relation in an algorithmic style. Yeah. It again is the same covariant and contravariant as we learned before. Good. And now we say that these three rules are equivalent of our declarative typing rules. May sound strange because we did have a lot more rules in the declarative world, and these three little rules do the same thing now for us. And for this, I'd like to implement this notion of soundness and completeness. You may have heard this before if you heard Eric Borden's lecture on code analysis, the DICA lecture. But in type systems, we do have a very special definition of these terms. They are related though. This is why they are the same. Sorry for that. I managed to turn off the mic. It's a new one. Good. So we say that we need to show soundness and completeness. Soundness and completeness tell us that these two rule sets are equivalent to each other. And we say that algorithmic rules are sound because every statement that can be derived from algorithmic rules can also be derived from declarative rules. That means, in other terms, the algorithmic rules do not prove anything new. That's soundness. And then the other direction is called completeness. And complete because every statement can be derived from the declarative rules, can also be derived from the algorithmic rules. That means that the algorithmic rules prove everything that could be proven before. Could be proved before. Proven, sorry. And in a short form, this is this. Yeah, this means that the declarative typing relation, subtyping relation, implies the algorithmic subtyping relation, and vice versa. This is soundness and completeness in just a little bit few characters. Yeah. Good. And as we do progress and preservation, we also need to prove soundness and completeness as a property, of course. And the way we do that is we use the lemmas defined in 611 and 612. This were the ones we had before. Good. So a subtyping algorithm. So now subtyping in an algorithmic form has a very unique property. It's so-called syntax directed. And the nice thing about that is we can really implement that, because if you just, we'll just quickly jump back to that slide with the rules. If you look now at the rules, the conclusions of these rules are very, very different. And they match syntactic structures very well. Yeah? So the SA error rule just matches anytime you have function. You have a function type. The SARCD rule matches in any type you have a record type, and the top rule matches in any other case where you just need to come to the top type. Yeah? So this seems like you can very much easily implement that. And here is an algorithm in pseudocode for subtyping. Yeah? You can now read these directly as an algorithm for checking the subtyping relation. So this is very, very neat. So this says, okay, some things are in a subtype relation, S and T. If T is top, then this is true always. So if you already know that the type on the right side is top, then this always holds. This is kind of the thing here. So you don't care about S actually anymore. Yeah, you don't use it in the premise or whatever. And then the other cases say, okay, else if S is this function type from S1 to S2 and T is this function type from T1 to T2, then you recurse into the subtyping algorithm for T1 and S1 and the subtype algorithm for S2 and T2. And then you do this for record types as well, which is just as an algorithmic encoding what you see before. As you've now implemented a fair amount of type systems in the labs, you should be very familiar with that kind of thing. So this you would can directly translate to Scala code, and else of course false, because this is not the case. If you look into the implementations that we had before, then you would really see that. Do we have that here? Nope. This works pretty fine. Oh yeah, and you just fail for anything else. Yeah, we don't return like false here, and in our type checker we usually fail. In the implementations that we did, I just checked the solution in the background, so don't worry. How we did it in this case, but you can also return false in the subtyping, algorithm here, as you can see, and then you have a judgment about whether S is a subtype of T. Algorithmically. So this was fairly easy to implement, as you can see. So you can now do the same thing as we did before and translate those things into algorithms. No? But with any algorithm, we are concerned with termination, because we do want type checking to terminate. We want to be it to be a decisive procedure, not to loop infinitely, not to diverge, and for this we need to show termination. So this says that this shows now the equality of the algorithmic subtyping rules and the algorithm. This shows, okay, if S is algorithmically a subtype of T, then the function subtype st will return true. If not, subtype will return false. And now this theorem, the termination theorem, together with soundness and completeness of the algorithmic rules, assert that subtype is a decision procedure for the declarative subtype relationship. And this also shows that they terminate. Why is that the case? Because if you look at the implementation here, you have basically four cases. The first case is the T-top case, which also always terminates. You have the last case, which also always terminates. So the only interesting cases are the two middle cases. So the first case for the arrow rule just recurses into subtypes. So this will eventually be terminate if the subtype in general terminates. So we need to look out for that. And for the records, you will see that this either returns true or false for these record types, or will recurse, and then the induction hypothesis holds, and this thing terminates. And because you construct this by a decision procedure that is sound and complete, this also helps your termination in that case. But let's look into this a little bit more closer. So here's the proof, or proof sketch to be true. So the first claim is easy to check. So you do straightforward induction on the derivation of this subtyping, of this algorithmic subtyping relation S and T. You already done this. You just need to case by case go through the rules and so on and so on. And do straightforward induction, as you all know. And conversely, it's also easy to check that if subtype S and T returns true, then also the algorithmic subtyping rules give you that derivation. So you just show the equality of the algorithm and the derivation so that your implementation actually implements what your rules say. But to establish a second claim, we now need to show that subtype ST must always return something, so that it cannot diverge. And this is what we've done just intuitively. So this can be done by observing that the sum of the sizes of the input pairs S and T is always strictly larger than the sum of the sizes of the arguments to any recursive call that the algorithm makes. And this is a classic way to show termination. So that the input size is always larger than the sum of the size of the arguments to any recursive call. So it does not get any bigger and it does not stay the same. It shrinks continuously. But since the sum is always positive, an infinite sequence of recursive calls is then not possible. This is a classic termination proof, as you would do in other algorithms. So if you've taken up some of the courses from the algorithm department, this should feel very familiar to you. And if not, you just make this clear yourself. You just look at the input sizes of the pairs. Look at this. You always get smaller types whenever you recurse into subtype. So the function type is deconstructed, the record type is deconstructed. So you should eventually terminate. Good. Thing is, now we have established 3 different systems. We have the declarative typing rules. We have the algorithmic typing rules, and then we have an algorithm implementing the algorithm typing rules. Why do we all need all of these? So why do we need to keep declarative typing rules when we now have algorithmic typing rules? This is a question for the audience. That's why it's blue. So do you have an answer for that? Why do we need all of these? Can we just go with algorithmic and be fine? We established we cannot just go with declarative because they cannot implement those. This is like a hard limit. But why not just go with algorithmic subtyping rules and be fine? Do you have an idea? Oh, and if it's not clear, that's the point where you type in your idea into the chat. Algorithmic depends on declarative. Yeah, they should be the same, so they depend on each other, I would say. But if they are so like dependent on each other, if one implies the other and so on, why do we need to keep around both? Oh. Yeah, algorithmic is only for subtyping, but so like the declarative, we can have declarative rules for subtyping as well. We started out with these in the last lecture, and we've just shown that they're equivalent. So whenever there is subtyping, then declarative calls algorithmic. Yes and no. So the declarative type checker, so the type checker that we now implemented at that point are declarative. So they follow declarative rules. We cannot do this for subtyping, as we just said. And then, like for subtyping, we call this specially prepared algorithmic solution. This is true though, but why do we need declarative subtyping rules? Yes, thank you, Kai. The proofs are easier with declarative rules. We would do, and you can try this if you like, if you would do a progress and preservation proof with algorithmic rules, we would actually have a very hard time to do that. It is possible, it is very tedious, because they are equivalent. You should be able to do this, but it's much harder to do. We still need to show that subtyping is well behaved, that it is following type safety, progress and preservation. And for this we need proofs. And for these proofs we actually need reflexivity and transitivity. We've used a lot of reflexivity and transitivity in the proof if you look it up. And this is why we need declarative rules. And this is why we do the little thing, the little proof that we did here of showing the equality of those two systems, because we still need both of them. It's very tempting to leave one of those out, but as we've seen, they are not that different. So it's actually a good exercise to do both and then show the equality of those. So actually this helps your implementation to stay on track. Yeah. Thank you for the answer, or for all of your answers actually, that led us to this point. Good, so now we fixed subtyping, but we also need to kind of fix, so this is all the S rules, but we still had that T sub rule that gave us a little bit of a headache. And we now need to import this into our type system as we see fit. Because we need to type terms such as this one. So this is a function that has that takes as an argument a record, and we give it a record that is not of the same type. And for this to work, we need subtyping. We need to fix tsub, because this kind of links our two type systems, the one for the general typing that we did for function, application, and definition, to the subtyping rules. And interestingly, function application is the only case where subsumption, so the T sub rule, is actually crucial. And any other case we can for any other case we can reorder the derivation tree. I'm particularly proud of the animation I did for that. I hope it goes over the stream. If not, let me know, then I'm making some kind of movie for that as well. So what we have here is an abstraction, and the next rule that we have up in the derivation tree is the T sub rule. No? And we can reorder this in this way, that we postpone the T sub rule just as the last, and then use the T abs rule together with the S error rule to actually show that this is true. And this is we can do for any kind of thing after the abstraction rule. So we can always push T sub to be the very last thing we do in the derivation tree. And this is a very interesting observation, because then we can include subsumption into function application. Because by applying these transformations repeatedly on abstraction, application, and other rules, we can now rewrite the typing derivations to a special form where T sub appears in two places. In only two places. So at the end of the right-hand subderivation of applications, so at the thing where we actually need to determine the type of the parameter, or at the very end of the whole derivation, as we've seen in the previous slides. And the interesting thing is we can actually delete the one at the end, so the second case, and no harm will be done to our result if we have a derivation assigning a type to the same term. The type might be smaller, but that is usually considered better. So this is very nice. Technically, from a theoretic standpoint, this is not the same. It is actually a little bit better to the intuition that we have. It is not the same though, but it is something that we can do, and in practice helps us a little bit even. How does this work? So this only leaves application. So the second case we just argumented away. So we only need to change the application rule for that. So this is the modified application rule. And as you can see now, this looks like the standard application rule, but instead of forcing T2 to be big T11, we just said, okay, this is a new type T2, which is a subtype of T11. And this is actually very close also to our intuition that says, okay, a parameter can be a subtype of a parameter can be a subtype of the requested type. So look at things like Java. So you request in the formal parameter of a function, you request an interface, for instance. You can never have an object of that interface, but you can have an object that implements that interface in form of an object, an instance of a class that implements this interface. And the funny thing now for the lambda calculus is that it entirely eliminates the need for our tsub rule. By just observing that we can push it to the very end, and the only interesting case is actually applications. We only need to include the contents of the tsub rule into the application rule, which is already syntax guided, and eliminate the need for tsub entirely. So we can just come out of this problem. And as I said, like, the new rule is already syntax guided, so we do not need to change anything for that. And we now have a definitive point where we want to, like, one definitive point in our type system where we want to check subtyping, and we can just easily do this at this particular point and just call the algorithm that we meticulously thought of. So full algorithmic subtyping looks a little bit like this. So this is the full algorithmic typing with algorithmic subtyping. So the tvar rule looks as you know it. The tapps rule looks as you know it. The tapp rule is now this modified thing where instead of having 3 premises as the normal tapp rule does, or 2 premises, in this case that the type is factored out, there is a call to the algorithmic subtyping relation. Then we have the TARCD rule, just typing records. So this is basically the same thing, but just exchanging standard typing by algorithmic typing, and the projection rule as well, unchanged. So the only thing where you actually have to change is in the TApp rule. Good. We've shown soundness and completeness for the subtyping. Now we need to do this for the general algorithmic typing rules that we just did. And the soundness for this is if the soundness for this holds if we can type something in the algorithmic typing, we can also type it in the declarative typing, and we can prove this actually by straightforward induction under algorithmic typing rules. So you just go case by case, and for sub problems you use the induction hypothesis, and then you're good. This is a proof as mechanic as you've seen before. The idea for completeness is now that we can show that that if a term T has a type T under the declarative type rules, then it has a better type S under the algorithmic typing rules. This is the small inequality that I talked about. So in algorithmic typing rules, we can actually find a smaller type, like a better type that matches this term. But as subtyping is in place, we're still compatible. So algorithmic typing assigns the smallest possible or minimal type. And this we can put into the rules for completeness, saying like, if we can type something in the declarative rules, then algorithmic typing rules for the same term give us a type S that must be a subtype of T under declarative rules as well. And this is how we show completeness. In order to make this much more useful than it is right now, we need to also take care of expressions with multiple result branches. Conditionals, for instance, or case expressions. There we had the case that we actually forced T2 and T3 to be of the same type. This is rather conservative, as you already seen. We discussed this sometimes in the exercise as well. And the problem here is that in a language with subtyping, this requires a little bit of more additional machinery to actually make that a little bit less, conservative, as I said before. Because you do want to loosen this up a bit. T must not be this type of T2 must not be the same type of can be a different type than T3, but at least you want them to be compatible of some sort. So to introduce these compatibilities, you use joins and meets. So in the T-if rules, the types of both branches have to be the same. We want to but we have already seen like many ways where these two branches may be of compatible types. Especially for records, we've seen that we can find something that works there for both branches. How do we do this for algorithmic types? We use joins or meets. And to calculate the minimal type of an additional conditional expression, of an arbitrary conditional expression, we need to calculate the minimal types of its then type. This is a join. It is called that way because it corresponds to the join terminology of two elements in a partial order. And this is because they are in a partial order, and the partial order is subtyping. And of course, when we are at that point, we can also define a meet. And the meet is, we say that the type M is a meet of S and T, written S as a meet of T, as M, if M is a subtype of S and M is a subtype of T for all L types that are also subtypes of S and T, L is smaller than M. Like L is a subtype of M as well. The join basically in the definition is the same thing but vice versa. There the join must be like T must be of U, then the join must be kind of the subtype of this. Meet is the supertype. Graphically, you can show this in a lattice. If you also have heard the Dicker lecture, a lattice will become very natural to you. And this is how it looks. So you have these types S and T, which are both record types, but they're not the same. And as you can see, the W and the Z differs. And if we leave that W or Z out and just have X and Y, which are both top types, then this is the join type of these. And the meet type of these will be the union of those types, of those records, basically, both carrying W and Z. So this is the meet of both types. And graphically, it's usually very helpful to do it in a way like this. Why do we do this? Because at some points we want to show compatibility of those types, and not arbitrarily, but specific compatibility of these types. So joins and meets are very, very important here. Yeah, so this is the join of S and T, and this is the meet of S and T. Yes. Wow. So the existence of a join and a bounded meet we need to show. This is helpful to say that they actually exist. And the lemma for this says for every pair of types S and T, there is some type J such that the join of S and T is J. And for every pair of S and T with a common subtype, this is the important part, they need to have a common subtype, there is some type M such that S meet M is the meet, is M. Sorry, S meet T is M. And this then provides us the existence of joins and bounded meets in that case. Why do we need this? Of course, for proofs, and of course, to show that this actually works in practice. Yeah. How do we factor this in now in the presence of subtyping? Well, this is the TA-if rule. This is basically the T-if rule, but using the join operator. So what do we have here? Okay, T1 must be of type big T1, which is again Boolean. This makes sense. We didn't change those. And T2 and T3 are of either big T2 or big T3. And now we need to bind these two together and say, okay, how are those types related to each other? Well, the join of both types is a type called T, which is then the result type of the whole expression. So whenever you have two types that are the same, the definition of the join gives you the same type again, because you can join, if you join a type with itself, you get the type itself. If you have a term that is less compatible with that, you get kind of the join of that. In that record, you would get the smaller record. And this is intuitively what we wanted anyway, so we're pretty much fine. No? The bottom type, this is actually where it comes. I started out with that. I'll come to this point again. The bottom type in algorithmic subtyping works in a way like this. So algorithmically, it is a subtype of all the types. And so if you check that, if bottom is a subtype of T, then you're fine. If you apply something, if you have a typing of an application where the type of the function is bottom, and then the result of the whole thing is bottom, because you don't know that anymore. And if you have a projection of on a record that is of bottom type, then the projection is also bottom. And so the intuition here is that in the declarative system we can apply something to type bottom to an argument of absolutely any type by using subsumption, and assume that the result has any other type. And similarly goes this for projection, as we just explained. So this is again just an application rules, the same thing as we had in the declarative rules, but like not in a separate rule, but just pushed into all of the cases of applications, so that we are syntax guided again. Good. Actually, that's it for today. That has been based on chapters 15 and 16 of the book. We will have some exercise about that. There will be a lab about subtyping as well. Is it the next one? Let me check. I think references are the next, but yeah, references are the next. Records and subtyping are the fifth lab that will come out on June 3rd. So in 2 weeks. So this would be pretty nice. Good. Are there any questions towards the lecture? Because we do have a lot of time today on our hands because we were so fast. This is good. Are there any questions to the lecture today, to the exercises that we had so far? Anything that was unclear to you? Please let me know. We still do have some time to discuss that right now. Good. So the course seems to be rather easy for you. Well, it's good if you all come along. Aha. The last sheet, last exercise. Is it possible to construct the example with assignment instead of using let? Ooh. So going back to the exercise. Yeah, that we discussed this day. I still have this here. Is it possible to construct something without a let? I think it's hard. Ooh. Well, you could do sequencing. No, then you don't have the labels anymore. No, I think you need sequencing and lets. I'm unsure, but on the top of my head, I would think now you do need a let. If someone comes up with a solution that does not require a let me know. Haha, pun intended. No, because I think you need actually the label to reference back to that as to alias that reference back. No, I don't. No, I think you need let. Well, again, if someone comes up with a good solution without a let, post it into Panda, please, or post it here into the chat if we're still on. A is ref 0, B is A is B. Well, how would you type this? This would be so for gamma it would be A is reference to nut, B is reference to nut, and A is reference to nut. I think this would be fairly easy to do statically. So the trick in the solution that I presented is actually like the difference of the typing, of the actual runtime typing, using functions and also dereferencing. And then the type checker needs to check the like in the Sigma needs to check the types for these functions, and then would get stuck in an infinite loop. For this, it actually can be done because you can start out and type from left to right, which you would normally do in sequencing, and say, okay, the A is a reference to nut, B is assigned A, so it must be a reference to A. Otherwise, also B is not constructed yet. And also, without a let, you do not have and also your assignment on the left side is not valid, because on the right side of an assignment you only have a value, not a reference. That's the term. You also do not have constructions for the reference constructions for B. So we actually don't know what B is. It's hard to do without a let, I think. did you say we can assign refs, but they will carry the position? Yeah, sure. Now a chat would be great. Like where I can actually see and hear you. Okay. Let me see. So the problem with that is we need to construct A first. We don't have any A yet. Syntactically, we don't know what A is. So you will have something like something like this. A equals ref 0. When you assign something like this, then A would be of type ref nut. You see? Because on the right side hand of an assignment, there's only just the value. Maybe, let me pull out the slides for that again, maybe. Good. So allocation is this. So we have a syntactic element on the left. Yeah. Maybe have a little bit of a longer look at the solution. I just go quickly over the reference operators, because this also was a little bit strange how you used it. Allocation means that we construct, or let me just quickly move to the rules for that, because this is just a construction and I need the final rules, which are here. This is the typing, this is evaluation. Good. So if you look here and see the rules for where do we start? eVerf v. So as you can see, you actually don't have something on the left hand side here. A term is basically just the reference, and to give a term a name, the only way to do this right now that we have in the lambda calculus is the let construct. No? Otherwise, you would have to use this reference at that point where you do it, and you cannot reuse it without a let. So let and ref are kind of intertwined in that way. And on the assignment side, that's also something that I wanted to show you. Pretty harder to see. Let's look at this. So the last rule here, oops, oh, this doesn't work. Okay, if you look at the t-assign rule here, you see that on the left side you have a reference. This was in your example good, but on the right side you have the type of that reference. So if you do an assignment that is so a colon equals ref 0, this would be then a would be a reference to a reference of nut, and not just a reference to nut. Good. If this is troubling you longer, maybe we start a post on Paul about on Panda about this, and refer to the next exercise sheet. Also repeats everything that we heard before, and also reference will be in there. More exercises on reference to get that a little bit stronger to be repeated. Good. Any more questions now that we have the time? Good. If that's not the case, thank you very much for today. I'll leave you today a little bit earlier. And remember, at 12 the new lab comes out. Again, 2 weeks, like in everything. But the bonus points progression, the points progression in the labs seems to be quite good. So I'm pretty happy with your results so far in general. So keep up the good work on that. The 7th lab will actually be, I'm just preparing that. The others also have already been prepared. The 7th lab will be particularly interesting and will be a little bit larger than the others. So if you are just here for the 50%, then maybe do all the labs from 1 to 6. And if you're in it to learn a little bit more, take some time for lab number 7, because this really sums up more or less everything in the course. Good. Thank you very much, and see you next week.